while sum comma CF. Sum comma CF. Next, what I need to do? We need to instantiate it. Okay. So for this is full order. Shall I take full order like this? Is it fine? A name, instantiate name, anything it may. Okay, I'm writing full order. Okay. Or you can write full order 1. No problem. Full order 1, no problem. So what I need to do? Shall I go port connection by define, then initial begin. Okay. Shall I go with the concatenation operator? Generating A, B, C value inputs A, B, C. This is equal to $symbol random. $random. Then let me give some sim time to print the output. Then what I need to do? Display what I need to display? A is equal to percentage B, 0B, tab space. B is equal to percentage 0B, tab space. Cin is equal to percentage 0B, then tab space. Sum is equal to percentage 0B, tab space. Cout is equal to percentage 0B. Then what argument I need to pass? AB, Cin, then sum and carry. Cout. This is Cin. This is Cin, Cout. Correct. Then end the initial begin in the module. Correct. Now let us run this program. Now A is equal to 1, B is equal to 0, Cin is equal to 1, what is sum is 1, carry is 0. If you consider this is LSB and this is MSB, so A is 1, 1 plus 0 is 0, 1. Again 1 plus 0 is nothing but sum is 1, carry is equal to 0. Now shall I repeat this part? Repeat this part 5 times, or let me repeat for 8 times. Let us check all the possible. Since I'm using $symbol random, I won't get the orderly binary representation, correct? 0, 0, 0, 0, 0, 1. Since this will generate the random values. Okay, I'll be repeating how many times? 8 times. 8 times I'm repeating this. This is 8 times with the different inputs A, B, C, C. This is my sum and this is my. So let us check this. This is 101 is nothing but 5. 5 carry is 1, correct? Again this is again 101. This is also 101. So this is 0, 1. 1 means what? 3. What is carry is 1. So 101 is 4. Carry sum is 1. 001 is 1. Sum is 1. Correct. Again this is 001 is nothing but 1. Sum is 1. So this is a program of full order using data flow model using operators. Correct. Now let us do same thing here for what? This is for 1 bit full order. 1 bit full order. Now to do it for, there was the one question I was asking, 1 bit off subtractor. Sorry, full subtractor, not off subtractor. This is a full subtractor. What is a full subtractor decimal notation, sir? Full subtractor decimal notation. Let us take, this is a full order. Full order. Full order. Now let us copy here. This is nothing but full subtractor. Full subtractor, what are the outputs, sir? Full subtractor, what are the outputs, sir? Difference is output. Difference is same as an sum. Correct? Then bar. So difference is decimal notations are 1247. This is a canonical equation of the 1247. And this last one is what? Minimized expression of the canonical equation. Then what are the borrow decimal notations, sir? Can you remember full subtractor? What are the borrow decimal notations, sir? 1, 2, 3, 7. 1, 2, 3, 7. Correct. So let us write the full subtractor. So this is my full subtractor. How many inputs will be there? 3 inputs. A, B. Shall I take B? So why I am writing B is nothing but if some 0 is not subtracted by 1, I need a bar. So that bar I will represent it as B. So this is nothing but bar. 3 inputs and 2 outputs, full adder, full subtractor. So 3 input means how many possible combinations you can fit? 8 possible combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. So this is a difference and this is the bar. So what is this? Full subtraction. 0 minus 0 is nothing but what? 0. Again 0 minus 0 is nothing but what? 0. So difference is 0, bar is also 0. 0 minus 0 is 0. Again the result of that will be minus with what? 1. But you can't subtract 0 with minus 1. So that you are taking bar 1. Now this becomes what? 1 0. 1 0 means 2. 2 minus 1 is 1. Here also 0 minus 1 you can't subtract. So you are taking bar 1. Correct. Now when you take the bar 1, this becomes 2. 1 0 means what? 2. So 2 minus 1 is what? 1. 1 minus 0 is nothing but what? 1. Did you understand? This is what? 0. You can't subtract 0 minus 1. So that bar is 1. So if I take bar is 1, this is 2. 2 minus 1 is 1. Again 1 minus 1 is what? 0. Here 1 minus 0 is what? 1. Again 1 minus 0 is nothing but what? Difference is 1. Bar, you are not taking any bar, bar is 0. Here 1 0 1. 1 minus 0 is 1. Again 1 minus 1 is, difference is 0, bar is 0. 1 minus 1 is 0. This 0 minus 0 is nothing but 0. Difference is 0, bar is 0. You can see here 1 minus 1 is what? 0. Again from the 0, can you subtract 1? No. So that you are taking the bar is 1. When you take the bar, that becomes 2. 2 minus 1 is 1. So for the difference, the decimal notations are 1, 2, 4, 7. For bar, what are the decimal notations are? You can see what are decimal. If I denote this into decimal notations, what are the decimal notations is? 1, 2, 3, 7. Correct. If I write the canonical equation, simplified equation, this is nothing but what? A XR, B XR, B. Correct. Bar expression is? What is bar expression? Let us construct the K-map to this. Correct. K-map to this. This is A, B, B in 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. What are the cells are ones in this case is? This is a K-map structure, correct? Graphical method. So 1 cell is 1, correct? Then 2 cell is 1, 3 cell is 1, 7 cell is 1. So what is the possible grouping is? 2 ones grouping is possible. This is a grouping. So what is the expression I will be getting for bar? So for this is nothing but A bar. B will knock out. You will be getting B in plus. For this is 3 and 7 grouping is B, B in, correct? Plus for this grouping A bar B. A bar B plus A bar B in plus B into B. So this is the expression for the bar row. Correct? Can you tell me what is the bar expression now here? What is the bar expression? A bar B plus B in plus A bar B in. A bar B in. Did you understand? A bar B plus A bar B in plus B in. So this is the bar expression. Correct? Did you understand this? Now, how to write a program to this? How to write a program to this? Shall I make this into what? Full subtracted, correct? So this input I am going to take what? B, B in. What are the outputs are? Difference and bar. Let me write difference and bar. So here input types are A, B, C, B in. This is difference. Outputs are difference and bar. This is difference. This is bar. difference and borrow. So this is nothing but same, correct? Difference is XOR operation. Then what is borrow expressions? A bar. This is A bar, correct? A bar means how to write A bar means what operator I can use? Feudal symbol, correct? Not operator means what? Feudal symbol, bitwise not operator. A bar being, again this is B being, B being, next is what? A bar being, A bar being. Difference? G being bar. Okay, you're talking about this one. This is B being. Okay. Here, this is B. This is nothing but what? Difference. This is bar. Bar. I can use the same test bench. Is it fine? So this is full adder, full subtractor 1 name. I am connecting the ports by default. In begin, this becomes random time generating ABB. Okay, this is the output. Now I'm going to change B to what? B, sum to what? Difference. Come to difference, then C out to borrow. Borrow. This is B, B. This is nothing but difference, and this is nothing but borrow. Borrow. Correct? Other things are same. I'm repeating how many times? 8 times. You can say 1, 0, 0. Difference is 1. Borrow is 0. Correct? 0, 0, 1 means 1. Decimal notation is 1. Or what is difference is? Difference is 1. Borrow is also 1. You verify with this truth table. That's it. This truth table. Okay. And this is again 0, 0, 1 means what? Difference 1 and borrow 1. 0, 1, 1, 0 means 3. Difference is 0. Borrow is 1. And then 0, 1, 0 is nothing but 2. Let us check this combination. 0, 1, 0 is 2. Difference is 1 and borrow is 1. Did you understand? Let us copy this result.
नहीं वो पढ़ाने वाला तो चलो ठीक है, हालांकि इतना लंबे
So this is a 1 bit full subtractor.
वो बोलेंगे कि अब है ना
Now we need to design.
आपने वो स्टूडेंट अप्लाई किया वो ऐसे
This is a 1 bit full subtractor. Now let us go with what is the other question is. Yeah, this one. So write a program of data flow modeling of 4 bit full adder using concatenation and place operator. How to do this? What is 4 bit full adder is? Parallel adder, right? 4 bit full adder. So let me quickly write. 4 bit full adder means what? Parallel adder. 4 bit full adder is nothing but parallel adder. How many bit adder means parallel? 4 bit parallel adder. How to construct the 4 bit parallel adder? Using full adder. Correct. How many full adders are required? 4 full adders which are connected in what? Cascaded form. Correct. This is a 1 full adder. This is a 1 full adder. 1 full adder. This is a 1 full adder. So what are the inputs to this is nothing but. Shall I take this is A naught? Correct. B naught, A naught, A1, A2, A3 are the minuend. Correct. B naught, B1, B2, B3 are the subtrahend. Correct. And then this is a full adder. How many inputs will be there? 3 inputs. So this is the input is coming from the previous stage. C in, or I can write what? C minus 1. If it is this is A naught, this is coming from the previous stage means this C minus 1. What is the output is nothing but some S naught. So whatever the carry is generated in the first stage full adder will be propagated to the what? Next stage. What is the carry? C naught. What is sum is? S1. And again carry is what? C1. What is sum to? This is nothing but S2. What is the carry is? C2. What is the sum is? S3. And this is nothing but what? C3 is out. So this is a 4 bit full adder, or we call parallel adder, or magnitude adder also. What magnitude means? 4 bit magnitude adder. Did you understand this program? Now this I have to design design data flow modeling for 4-bit full adder using concatenation and place operation. How to do this? Can you write a program to this? Shall I use this is a full adder 4-bit full adder. What are the inputs to this? Is A, B, C in. Okay. So let me do one thing. If I go line by line typing, so it will be easily understandable. If I start editing, somewhat confusing for you. Okay. Let me write full adder 4-bit full adder. So what are the inputs to this? Is A is a one input, B is a one input, C is a one input. What are the outputs, sir? Sum and carry, C out. Let me take sum and C out. Or if I take S and C, is it no problem? Let it be like this only. You can easily understand what are the ports are input port and output port. Then you tell me what are the input ports are? Input sign, what is the vector of A and B? How many bits you are doing? 4 bit, right? This should be what? 3 down to 0 of what? A comma B. A comma B. Again, input. How many bits you need C in? 1 bit. This is C in. Correct? Then output are what? Outputs are what? Sum is 3 down to 0. You can see in this diagram, you need A0, A1, A2, A3, 3 bits. B0, B1, B2, B3, 3 bits. C is a single bit. These are nothing but a wide data type now. C0, C1, C2, C3 are what? It is a interconnection between the what? Circuit. I can consider three C0, C1, C2, C3, C2 and C3 are the wide data type. This is C3 is nothing but C out. This is not a wide data type. C3 is nothing but a C out. Correct. Now, how many bits sum is? 4 bit. S0, S1, S2, S3. Therefore, I can write this is nothing but sum. 3 down to 0 sum. Correct. Then C out is equal to what? Output. Another one is output. This is the output. Correct. C out. Correct. Then what are the wide data types? C0, C1, C2, C2. That's it. So whether we are using any wide cell C0, C1, C2, we are not using in this case. So I'm asking to do this using concatenation operator. No need of wide. When you are modeling the gate level, then you need C0, C1, C2. Correct? So since I'm doing this using what? Continuous assignment, I don't need wide data type C0, C1, C2. So I'm adding 4-bit minuend, 4-bit subtrahend. I'll be getting sum, 4-bit sum and 1-bit C out. So how to do this? How to do this? What I need to do here? Flower bracket. What is the use of this flower bracket? Concatenation. What concatenation I want to do? C out, correct? C out comma sum. This is equal to what? Just you do the addition operation. A plus B plus C. A plus B plus C. Correct? Now this will take 4 bit, this will take 4 bit, this will eventually 1 bit. Okay. It will do 4-bit addition operation. And 4-bit sum is will be assigning to what? This sum. And last 1 bit is assigning to what? C out. It is as good as concisely we reduce the code. If you remember, okay, in next session I'll be talking about the gate level. To model the full adder, 4-bit full adder, first we'll be instantiating the full adder. Again we are instantiating what? Half adder. Hierarchically we are doing. But here I can easily do using this operator, concatenation operator. So A plus B plus C. So this is nothing but parallel adder. Okay. So now, then what I need to do? In the module. That's it. Correct. Now I need to write the test bench to this. Module TB. Okay. Module TB. Then what I need to write? Rex 3 down to 0. Correct. A comma B. A comma B. Sorry, A comma B. And reg C. Then while 3 down to 0 what? Sum. Again y, scalar is what? C out. Next what I need to do? I need to instantiate the design file. So let us make a order. Then let me do port by connection default. Now I need to generate the input and apply the input to the design file. Correct. For that I should start with what block? Initial block. Initial begin. Correct. Shall I use a comma concatenation operator? A comma b comma c. This is equal to dollar symbol random. Is it fine? Then let me give some sim time to print the result. Dollar symbol display what I want to display. A value, correct? 0b, top space, b is equal to percentage 0b, then top space, c is equal to percentage 0b, correct? Again what I need to print? Sum. Sum is equal to percentage 0b, then top space, c out is equal to percentage 0b. Now what are the argument I need to pass? A comma b comma c in comma sum comma c out. Then end this in the initial begin in the module. Correct. Now let us run this. So A is how many bits it is generating? 32 bits, right? So A should be 4 bit and B should be 4 bit. So the B I am using. Let us remove this 0B. Let us remove this 0B. Now I am going to run this. Now A is 1001. B is equal to what? 0010. So 1001 is nothing but decimal notation 9. And 0010 is nothing but 2. And C in it is taking as, let us give the tab space and run this. C in is 0. So 9 plus 2 means what? 11. So let me print this in the decimal. 9, decimal is also in decimal. Let us print B in binary, because since it is taking only 1 bit, right? Sum is in decimal, C out in binary. Okay. Now let us run this. Now 9 plus 2 is nothing but sum is nothing but what? 11. Correct. Now let us repeat this for 10 times. Repeat 10 times. Begin. And where I need to end? Here. End. Now let us repeat this. So 9 plus 2 is 11. 4 plus C in is 1 here. Correct. 4 plus 1 means what? 5. Let us take this one. What is my A is? What is A is? A is 4. Means this is 0. Correct. 1, 0, 0. B is nothing but what? 0. Subtrahend is nothing but 0, 0, 0. What is C in is nothing but in this case is, you can see this second one. Minuend is 4. Subtrahend is how much? 0. What is C in is? 1. Now what is the result is? 5. Now can you do this operation? What is 0, 0, 1 is nothing but, this is 1. 0, 0, what is carry it is generating? 0, 0, 1 carry is 0. 0, 0, 0 means what? 0. And what is carry is? 0. 0, 1, 0 means what? 1. What is carry is? 0. 0, 0, 0 is nothing but what? 0. What is C out is? 0. This is nothing but 5. What is C out is? 0. What is C in is? 1. So it is doing 4 plus 1 is nothing but what? 5. C out is 0. So in this case, minuend is 0. Subtrahend is how much? 4. 0 plus 4. What is C in is? 1. 5. Result will be the 5. 3 plus 1 is 3 plus 1 plus 1 means what? How much? 5. Again this is 8 plus 6 means what? 14. 14 plus 1 means what? 15. 12 plus 16 means how much? 12 plus 16, man. 18. 12 plus 6 means what? 18. 18 plus 1 means what? 19. So 19 in binary. What is 19 in binary? 19 in binary is nothing but, correct? 19 in binary is nothing but 10011. So your sum will take how many bits? 4 bits. And your Cout, this is your Cout. This is your S0, S1, S2, S3. This is nothing but what? Cout. This is a 19. So, but it is sum taking how many bits? 4 bits. So 0011 means what? 3. So Cout is equal to 1. This is the result I am getting here. 12 plus 6 plus 1 is 3 and Cout is nothing but what? 1. Are you understand? Is it clear here? What about next one is 3 plus 2 means what? 5. 5 plus 1 is nothing but what? 6. Again, 0 plus 9 is what? 9. 9 plus 0 is nothing but what? 9. So 8 plus 0 is 8. 8 plus 1 is nothing but 9. Again, 8 plus 6 is nothing but 14. 14 plus 1 is nothing but 15. Cout is equal to 0. Only I am getting Cout is equal to 1 for what term? Main end is 12. Subtrahend is, and if you make Cin is equal to 1, so 12 plus 6 is 18, 18 plus 1 is 19, 19 in binary is nothing but 10011. Sum will takes 4 bits, so that 0011 is nothing but 3 and Cout is nothing but 1. So 10011 is nothing but 19. Did you understand? Are you clear? How to do? What order it is? What order we are doing here? Parallel order. Now I want to make this into 8-bit order. What I want. So I don't need to change all the time here 7, again here it is 7, here it is 7. I don't need to do a lot of customization of my program. Okay, so how to do this into the 8-bit order? By including the parameter to the program. Correct? How to do this? Or you can use the tick define compiler directives. Create a macro. Right? So let us create a macro here. How to create a macro? Ticker. Correct? Ticker define. This should be coming out of your module scope. Correct? All the compiler directives should be coming out of what? This is your module scope. Correct? This is your module scope. This compiler directives will come what? Out of the module scope. Ticker define. Shall I make this is into depth? Usually macros are created represented in what letters? Capital letters. Depth is nothing but shall I make it to what? 8. Now what I am going to do, how to make this into the 8-bit order? 8-bit order. Now this is 7 down to 0. To make this 7 down to 0, what I need to do? I should use the depth. Tick depth, correct? Depth minus 1. Correct? Now A is 8-bit, B is 8-bit. And what is my sum is? Sum is also 8-bit. Tick depth. Depth minus 1. Did you understand? Again, where I need to change here also? Yeah, this is minus. Depth minus 1. Here, I need to change this into what? Tick depth. Depth minus 1. Here also sum I need to change what? Tick depth minus 1. Correct? By changing this macro, I can make this into 4-bit order. Correct? Let us make first 4-bit order, then we'll go into 8-bit. Correct? Is there any other things I need to change? No. Now this is my 4-bit parallel order. Now I am going to change this into how many bit order? 8-bit order. I will say this is my 8-bit order. Okay. Now I want to make this into what? 16-bit order. This is the beauty of the digital design, a digital system. See, you can design higher order module using lower order module with the less effort. Where the same case is not true in the analog design. Effort will be the double, not it is directly proportional. Okay, it is double of the proportional. This is one of the beauty of the digital system. You can design higher order design using lower order by replicating the circuit. So parallel order can be easily designed using what? Full order. Full order can be easily designed using what? Half order. This what? Replication is allowed in the digital system so that the design of the digital circuit is easy compared to your analog circuit. And also one more advantage is that it is less prone to the errors. Error handling is easy in digital mode. Now you can, by changing this macro depth, you can make this into how many order? Different order, 16-bit order, 32-bit order, 64-bit order. Even I can make 5-bit order also. Correct? This is my 5-bit order. Did you understand? So by changing this, okay, let me print this in the binary, then you will be understanding. A is now 5-bit, B is how many bits? 5-bit. What is my sum is also 5-bit. Let me print this in the binary. How many bit order I am doing? 5-bit order. A is equal to 5-bit. You can see. This is a 5-bit. B is also 5-bit. Correct. 5-bit parallel order I am doing. This is my what? Sum 5-bit. And this is my Cout is 1-bit. Did you understand? So you can make this into 6-bit, 7-bit, 8-bit. Usually we will talk about 2 power 8. Correct? 4-bit parallel order, 16-bit, 8-bit parallel order, 16-bit and 32-bit, so on. Did you understand? So what extra thing I am modifying to this program, customizing this program? What I am doing? I am using one of the compiler directives. And what compiler directives I am using? Tickdef. Now we are creating a text macro. Now what is macro name is? Depth. Then you can pass the value to this time. I don't need to changing always going inside the program and changing the width of A, B and so on. What I can do, I can use the compile directives. Then I create the macro. By assigning the value to this macro, this program works according to my macro. This is clear? This also you can do using what? Parameter also. Using parameter also you can do. Correct? How to do using parameter? Let us copy this program. Using parameter. How to do using parameter? What is the use of the parameter keyword? What is the use of the parameter keyword?
Constants into module.
You define the constant into the what? Module, right? What keyword I can use for this is parameter. Shall I use the depth thing? Parameter, I am creating this is depth is equal to 4. That's it. So this should be defined inside the scope of the module or outside the scope of the module? Inside. This should be defined inside the scope of the module. Now this will be working as a 4-bit order. This is not tick content, correct? This is not a compiler directives. Let me remove this tick. There is a syntax error in the per 4. This should be end with the what? Semicolon. Still it is still. Here also I need to initialize what? Parameter. So we have a one concept, parameter overriding. So parameter overriding. See, here I am defining the parameter. What is the parameter constant value? Is 4 here. Correct. So we can override the parameter. There are 2 techniques on that. Using depth parameter and overriding parameter using hash. That we'll see later. Okay, I don't want to make confusion right now by doing that. Okay, so we'll go step by step. Then you'll be understand. So without changing the parameter value of our design file, I can override it by including a parameter will be overriding by including the test methods. Did you understand? Are you clear? Now that we'll see later. Now this is using parameter. Or you can, now I want to make 8-bit order. What I need to do? I need to make a parameter depth is equal to 8. Did you understand this? Okay, let us copy this code. So first one using what? Tick define. Using macro, correct? Tick define using macro. And this is using what? Second way we are done using what? Using parameter. How to understand this? How to design the 4-bit order, 4-bit full order using data flow modeling. Okay. Now let us go to the next one. Today we'll address all the combination logic circuit. And after done with the combination logic circuit, we'll go to the sequential. Okay. Now we address the question of 4th question, 5th question. Okay. Then we'll go with 6th question. So before going to 6th question, shall we go with the 4th question, 7th question, because 7th question is relating to the order circuit. Since we are talking about order circuit, let us go with this. So write a program of data flow modeling a 4-bit carry look ahead order. So there are certain advantages of this order over your what order? Parallel order. Now coming back to your parallel order. So what are the limitations of this parallel order? Can you mention the limitation? Carry delay, right? Carry delay. Total, how many number of propagation delay? N times of full order, right? There are 4 full orders I am using. N is nothing but number of full orders. Let us take N times of TP. What is TP? TOP is nothing but propagation delay of 1 full order. Inside there are gates will be there. Gates also lead some propagation delay. I'm not considering that. I'm considering that what is the propagation delay of 1 full order. So this second full order will operates only whenever this carry will get correct. At what time this carry I will be getting? Suppose if I'm taking TP is equal to 1 nanosecond, correct? After 1 nanosecond only this C out I'm getting. Some S0 and C0 will be landed after what delay? 1 nanosecond. And then here S1 and C1 will be landed after what? After this one. If I consider this is nothing but 1 nanosecond. Again C2 and S2 will be landed at what? After what? 1 nanosecond of this. And this will be what? 1 nanosecond. Total to get S0, S1, S2, S3 and then C3, it will take how many nanoseconds? 4 nanoseconds. Correct? So we are talking about high-speed circuit nowadays. It should work on with the what? Picosecond level. Correct? All computations can be done at picoseconds. So this is one limitation factor we can see. See, parallel order works fine. It gives me the correct result based upon my menu and subtract. There is no problem with that. Result is giving. But if I think in terms of speed is a limiting factor here in the parallel order. So this is what the trade-off in the market will be going on. If you start
नहीं ऐसे कह रहा हूँ कि सीनियर मतलब टीचरों में से जैसे पढ़ाई लिखाई में तो
you get the less speed device. You pay more amount, you will be getting more speed device. You pay 8,000, you will be get 4 GB. If you pay 10,000, 4 GB. For example, 20,000, 10K, 4 GB, 20K, 8 GB. For what you are paying for here?
अच्छा
Future means speed.
तो सही है ना वो सही है
Speed you are paying. Okay, this is no problem. If I am compromising with delay, I can go with what? Parallel order. So no, I don't want compromise on delay. I need high speed circuit. Then what we need to do? We need to invent for high speed. I should work the operation, 4-bit parallel operation less than this nanoseconds. So that is better than this. Right? This is how keep inventory is going on all this. The circuits in digital circuit, we have started addressing the delay and the area. So that invention is keep going on. So the one which is giving 8 GB RAM, they will be not using this because of the delay here. So they will go with what? Fast carrying adders.
वो तो है.
Fast order circuits. There are many fast order circuits are there. Each fast order circuit having their own advantages and own disadvantages. Now, if I talk with respect to the parallel ladder, what is advantage is? What is advantage is? Building up the circuit is easy. But if you talk in terms of speed, speed is a limiting factor in the parallel ladder. But it gives me the result, correct result. But more delay, more propagation delay. That's why we keep inventing on what? High-speed circuits to addressing all these problems, propagation delay problems. Correct. So one such order is nothing but a carry look ahead order. Carry look ahead order. Carry look ahead order. What is this carry look ahead order is? Let me see it. This is my 4-bit order. As soon as my menu end subtrahend is available, I know what is my menu end. Say for example, menu end is 10001, like 0010. This is my menu end. This is my subtrahend. So to do this in this parallel ladder, to do this first I need to check C minus 1, correct? C minus 1, suppose if I am taking this is becomes 1, and whatever the carry is generated, it will be propagated to what? Next MSB bits, again next MSB bits, next MSB bits. So I will design a logic such that as soon as my menu end is available and subtrahend is available, I am going to predicting for this menu end and this subtrahend, I am going to predicting what is the value of C0, what is the value of C1, what is the value of C2, some sort of prediction. If I know that, as long as I know that what is menu and subtrahend, so that I am finding what is C0, C1 and C2, so that I can do the addition operation less than the 4 nanoseconds. So that order is nothing but your carry look behind order. Pre-computing the value sum. Name it implies. Carry look means I am looking ahead. Before computing my sum, I am going to looking what? Pre-computation of what? C0, C1 and C2. That order is nothing but a carry look ahead order. Okay, only this is not there. There are many carry look ahead orders. I mean fast carrying orders. Okay, carry skip order, carry propagate order, okay, carry save order. If you are list, if you search, you will be getting 20 to 25 fast carrying orders will be there. Okay, each order, okay, we won't specify that only this is a good. There are good at some perspective and there are bad at some perspective. Okay, each algorithm have own advantages and own disadvantages. That will be used based upon, I said trade-off. What is meant by trade-off? In the market, in terms of electronics market, trade-off is nothing but wrong. You pay the less amount, get the less speed circuit. Pay the more amount, get the high speed circuit. So one who is getting less speed circuit, they might have using this parallel ladder. No, I don't want to compromise with the speed. I can go with what? High speed circuits. Did you understand? Now let us see that how to design the carry look order. What is carry look order? Pre-computing of the carries. So how to do pre-computing of the carries? Now we will see. Okay. So if I write the full order circuit, this is my full order. This is my input. Shall I represent this is AI and BI, and this is nothing but what? Some SI, and this is nothing but CI plus 1, carry. This is nothing but what? CI minus 1. It is coming from the previous stage. This full ladder I am representing in general form. Okay, in general. If I is equal to 0, what happens? A0, B0, S0, C1. This is nothing but what? C minus 1. It is coming from the previous stage. Correct. If I write the truth table to this, so I am going to write AI, BI, this is CI minus 1, this is my some SI, okay, this is CI plus 1. So there are 3 inputs, how many possible combinations? 8 possible combinations. 8 possible combinations. What is sum is? 0, 1, 1, 0, 1, 0, 0, 1, correct? What is carry is? 0, 0, 0, 1, 0, 1, 1, 1. Correct? So sum is nothing but it is XOR operation. SI I can write what? AI XOR, BI XOR, CI minus 1. Correct? What is my carry expression? CI plus 1. What is my carry expression? You can see, if you notice this clearly, this truth table of full order, this is a carry expression, right? This is the one, wherever it is true function, right? If I'm talking about sum of SOP form is nothing but true functions. POS form is what? False functions. If you look at this combination, what you can understand from it? Carry is nothing but 1. This combination, carry is nothing but 1. What you can understand here? What you can understand? So here A bar, correct? This A bar, B, and C minus 1 is nothing but what? 1. Correct? Here A, B bar, what is C minus 1 is nothing but 1. So this I can write XOR operation. Correct? Now look at the other two combinations here. When carry is equal to, what is carry is equal to 1 here? It is A into B, irrespective of what? By C minus 1. So that what logical expression I can write for this CI plus 1 is nothing but. What logical expression? A into B, irrespective of the C. I can write this is nothing but AI into BI, irrespective of the what? C. If C is 0 or C is 1, always my carry is what? 1, 1. Correct? And what is one more combination is? A bar B, right? A bar B, A B bar is nothing but my XOR operation. Correct? I can write plus AI XOR BI into what? CI minus 2. This is a carry expression I can write for this. Correct? Carry is 1 when A XOR B. A bar B plus A B bar into what? See, when A bar B plus A B bar I am writing what? XOR operation. Are you understand this? This is the expression you are using to build the what? Full order, correct? Full order using half order. This is a carry expression used to build it. Did you remember? This is the logic here. Carry is equal to 1 when A bar B plus A B bar into C. And then carry expression output is 1. A and B irrespective of the one. C. Correct? These are my sum and carry expression. What is sum expression is? A XOR B XOR C. Correct? What is my CI plus 1 is nothing. A into B plus, correct? If I am removing this I, it is nothing but what? AB plus A XOR B into CI minus 1. Let me write this equations here. Sum is nothing but AI, in general I am writing AI, BI, XOR with what? CI minus 1. Correct? What is carry expression is? CI plus 1 is equal to what? AI, BI plus AI XOR BI into CI minus CI minus 1. Correct? So, here carry is, this we call it as carry generation. This is the bigger point. Carry generation. And this we call it as a carry propagation. Carry propagation. Carry generation shall I write this is nothing but GI. GI indicates carry generation. This is nothing but a carry propagation. This I am going to write as P. Did you understand? So this equation I can write one. Ci plus 1 is equal to what? GI carry generation.
join किया
A into B carry generation will happen. plus
इसलिए मैं तेरे को कॉल किया
What?
मैं तो अगर नहीं है तो
A XR
ठीक है
B
ओके
is nothing but carry propagated into what? Ci minus Ci minus 1.
मम्मी
Now what is a GI?
पता ना क्या करना है
What is GI? AI into BI. What is PI? AI XR BI. Correct? If I put I is equal to 0, what is G0 is equal to? A naught into B. I is equal to 1. G1 is equal to A1 into B1. I is equal to 2. G2 is equal to A2 into B2. I is equal to 3. G3 is equal to what? A3 into B3. Did you understand? What about the PI? What is PI is? When I is equal to 0. A naught XR B naught. I is equal to 1. This is P0. P1 is equal to 1. A1 XR B1. I is equal to 2. A2 XR B2. Again, I is equal to 3 means what? P3 is equal to A3 XR B3. Did you understand? I am just substituting I value for G naught, carry generation and carry propagation. Correct? If I know this, if I know what is A naught, A1, A2, A3, B naught, B1, B2, B3, I can generate the G naught, G1, G2, G3 using AND operation. Correct? I can generate what? P naught, P1, P2, P3. If I know what is C minus 1, I can computing the values of C naught, C1, C2, C3. Did you agree me? I can compute the what is a carry. As I know that what is a main and what is a subtrahend, using this carry generation, carry propagation, I can compute the C naught, C1, C2, C3, so that all full orders I can operate at the same time, same TP. So that essentially I can reduce what? Delay. This is a carry look add order is quite good than your parallel order. It reduces the what? Delay. But again, there is some limitation in carry look and order. Don't think that this is also good. As we reduce the delay, but few other disadvantages. Let me mention what are the disadvantages and options. Okay. Now this is what G naught, G1, G2, G3. This is not P naught, P1, P2, P3. How to generate the carry? What is carry expression is? This is Ci plus 1 is equal to what? Ji plus Pi Ci minus 1. If I put I is equal to 0, C1 is equal to what? 0 plus 1 is nothing but C1. Correct. This is nothing but what? G naught. This is G naught plus P naught plus 0 C minus 1. Correct. So what is G naught is? A naught into B naught. Correct. If I write this is nothing but A naught into B naught plus A naught into XR B naught into C minus. If I put I is equal to 1. This is C2 is equal to what? G1 plus, this is G1, right, sir? This C minus 1, right? Yeah. C1. G1 plus P1 plus C1. C0. Then where I'll be getting C0? Ci plus 1 is nothing but this is 0 means when I is equal to 0, this becomes 1. When I is equal to 0, this becomes 0. Yeah. This is the next carry. This is correct only, right? This is coming from the previous stage. I'm writing C minus 1. Correct. Now coming back to here. So this is G naught plus P naught into C minus 1. I'll be getting C1. The mistake one I did here is, the mistake I did here is this is nothing but CA, not CA plus 1. This is CA minus 1 is coming from the previous stage. This is nothing but what? CA. You take this as a CA. This is CA. Again here also, this is also CA. CA. Now it is coming to this equation now. This is CI. When I is equal to 0, now this becomes what? 0. C0, G naught plus P naught, C minus 1. Already I know that what is C minus 1. Correct. Again when I put I is equal to 1, then this becomes what? C1. C1 is equal to G1 plus P1 into what? C naught. I know what is a C naught, right? C naught is nothing but this is the one. This is equal to G1 plus P1 into 1. G naught plus. What is C naught value is nothing but G naught, right? Okay, let me substitute here. What is C naught is G naught plus P naught into C minus 1. This I can write what? G1 plus P1 into G naught plus P1 P naught into C minus 1. You don't understand? Now when I is equal to 2, this is C2 is equal to what? G2 plus P2 into what? C1. In this equation, substitute the C1. So let us substitute this. This is C2 is equal to what? C2 is equal to P2, G2, correct? G2 plus P2 into C1. What is C1 is? What is C1 is? C1 is this is the one. G1 plus, correct? G1 plus P1 into C naught. Correct? Oh, sorry, G naught. G naught. Again plus P1 into P naught into C minus 1. If I simplify this, C2 is equal to what? G2 plus P2 into G1 plus P2 into P1 into G naught plus P2 into P1 into P naught into C minus 1. Did you understand? Similarly, when I put I is equal to 3, this is what? C3 is equal to G3 plus P3 into C2. Now substitute the C2 in this equation. What is C2 is nothing but G2 plus P2 plus G1 plus P2 plus P1 plus. So P1 P naught G naught plus P2 P1 P naught into C minus. Correct. If I simplify this one, I am going to get G3 plus P3 into G2 plus again P3 into P2 into G1 plus this is P3 into P2 into P1 into G naught plus this is P3 P2 P1 P naught into C minus. Correct. What is P naught is? A naught X naught P naught. What is P1 is? A1 X naught A1 X naught A1. P2 is A2 XR B2. P3 is what? A3 XR B3. You know what is G naught G1 G2 G3. You know what is P naught P1 P2 P3. So we are using extra hardware, extra logic to addressing that delay. This is the extra. I am computing. As long as when variant is available, subtrahend is available, I will be pre-computing the values of what carries. C naught, C1, C2 and C3. So these are the logical expressions to computing what? Computing of what? Carries. So this is nothing but carry loop and R. Are you understand? Now we got C naught, C1, C2, C3. You know what is G naught, G1, G2, G3. We got P naught, P1, P2, P3. Correct. Then we need to computing the sum and the average. So these logical expressions. So again, what is the limitation of this carry look add order is, now look at your carry expression, C0, C1, C2, and then C3. What you can see, the problem, basic problem here is, here 2 input AND gate, correct? Here 3 input AND gate, here 4 input AND gate, here 5 input AND gate. Imagine it is 8-bit carry look AND order you are doing. Same computations. So there is uncertainty in the digital circuit. You are building the circuit with 2 input gate, 3 input gate, 4 input gate, 5 input gate. So there is uncertainty, means there is a problem of fan in and fan out problem. So there is a typical value for the gates. You should use only 4 input gate. If you go behind 5 input and 6 input gate, fan out problem emerges. That will not drive the correct voltage level at the output. Fan in and fan out will affect the carry look and order. Because you can see my carry expression will be having what? Different. There is no uniformity, right? Uniform circuit is not there. 2 input, 3 input gates, 4 input and 5 input gates. There is uncertainty, the gates usage. That leads to fan in and fan out problem. This is limited. This is, we can say that quite good than what? Parallel order. But constantly there is a problem called fan in and fan out. Did you understand? Now you tell me what is some expression is. What is some S0 is? What is some S0 is? A0 XR A0 into C minus 1. These are the carry expressions. Correct? Now use this expression to build a carry look and order. 4-bit carry look and order. Can you write a data flow modeling to this? Write a data flow modeling techniques to this. Are you understand what I said? Now can you write, unless student, can you write a program to this? Four-bit carry look and order. What I need to start with? Module, correct? So module name, look ahead, order. Is it okay? Or let us write CLA, carry look and order. CLA is carry look and order. What are the inputs to this? A comma, B comma, CL comma, sum comma, CL. Sum comma CL. So what are the inputs to this? Input are A comma, but this should be what? We are designing for 4-bit. 4-bit carry look and order. This should be A comma B. A comma B is 3 down to 0. Then input 3. Scene. Input is scene. Then output 3 down to 0. Sums. Then output is C. Correct. Then what are the wire data types here? P0, P1, P2, P3, P0, G1, G2, G3, and then is it C0, C1, C2, C3? So I can write wire is G0. Sorry. Wire is what? G0, G1, G2, G3. And then P0, P1, P2, P3. Next what? C0, C1, C2, C3. These are the wires. Now I should start writing the data flow modeling. Assign. Let us write for G naught. What is G naught is? G naught is equal to what? A naught and correct. B naught. Correct. Next, what I need to do? I need 4 assign.
We can give FA G equals to A naught and B naught.
Comma. Yeah, like this also you can do.
Okay.
Comma.
Then we
No need to assign like this. I can write this is G1, A1, B1. This is also fine. Comma. Then I am going to write like this. This is G2, correct. A2, B2. Yeah. Yeah, you can do that also. You can make this as vector, then you compute the what? A and B operation. Then you take A naught, A1, G naught, G1, G2, G. You can improvise this program how you want to. Let me go it according to what logical expressions I am generating. Later you see that how possible you can do this. Mentioning the vector for what? G naught. How you can do, you can think later. Now this is G3, correct? G3 is nothing but what? A3 and B3. Now let us check for the syntax error.
पहले 3 की जगह पहले ये काम करना था
I am writing this is 3 down to 0, right? This should be A of 0, like this. B of 0. Since I have declared this as what? Vector. A of 1 is nothing but B of 1. This is A of 2. This is nothing but B of 2. This is A of 3. This is nothing but B of 2. Now it works fine. Correct? Now I need to generate what? Assign. What I want to do? P0, P1, P2, P3. This is, sorry. That I will be modifying this, copying this, then I will modify this line only. This is P0. This is what I need to do. XR operation, right? A0 XR, B0. G1, P1 is nothing but 1. P1 XR, B1. This is P2 is nothing but A2 XR, B2. This is nothing but P3. P3 is nothing but 1. A3 XR, B3. A3 XR, B3. Now we're done with the carry generation and carry propagation. Now we need to generate the what? C naught, correct. What is C naught is equal to? C naught is equal to what? G naught plus means what I need to use? R operation. P naught and C. P naught into C. So let us check for the syntax. This is correct. Again, what I need to do? Assign C1 is equal to what? G1 R P1 and C naught. Is it C naught? Now after substituting the C naught, you tell me. G naught. Is it G naught? Alright. G1. No. P1 and G naught. Okay. G naught, okay. Again, this is R. P1 and P naught and C. Correct? C naught. C minus 1 I am taking as C. Assigned. Next what I need to do? C2. You tell me the final expression. G2 or P2 and G1. Again, this is R. Okay. P2 and P1 and G0 or P2 and P1 and P0 and C. Did you understand? Again, assign C3. C3 is equal to what? G3 or P3 and G2 or P3 and P2 and G1. This is R. P3 and P2 and correct. P1 and P0. Correct. P0 is there. P0 and C. P3, P2, P1. This is G0. Okay. C is not there. In C. Okay, yes. You know, one more product term is there. Okay. This is C and is not there. Again, this is R, correct? R with P3 under P2 under P1 under P0 under C. Then ends. Correct? Now let us check for the syntax again. Now we generated the G0, G1, G2, G3, P0, P1, P2, P3. Then we are computing C0, C1, C2, C3. Now what we need to do? Sum. S0, S1, S2, S3. What is sum is? Assign sum of 0, right? What is sum of 0 is equal to? P0, right? P0 means what? A0 into B0. This should be XOR with what? C. Again, let us write in same line. Sum of 1. What is sum of 1 is? P1 XOR C0 C0. C0. Again, next term. Comma. Sum of 2 is equal to what? P2 XOR of C1. Let me give the tab space. Okay. Again, this is C1. Again, sum of C3 is nothing but what? P3 XOR of C2. Yeah. Again, this is for sum. Then what is C out is? Assign C out is equal to what? C3. Assign C out is equal to C3. Now this is a carry low kind order. Let us check for the syntax error, line number 18. Okay, I am writing sum. Assign sum 0. Sum of 2 is equal to, okay, I have given the semicolon, it should be common. Now this is our design file for the carry low kind order. Now I can use the same test bench which I am using for the 4-bit parallel ladder. All I need a minuend, 4-bit minuend, 4-bit subprime. Then I need a return. Sum and CL. So I will be using the same test bench which I am using for what? Huh. Okay, sorry. I think this is the one. Alright. Okay, let's copy this test bench. This is my design and this is my test bench. Here, let us remove this. Okay, I will be keeping this into what? 3. This also 3. Or later you can modify by using tick define, create a macro and make that 4-bit, 8-bit orders, different orders. Okay, now let us run this. So I need properly not instantiating the design file. This is CLA. Now this is my someone carry. Let me print in decimal to verify the answer. AB in decimal, and some also I am going to print in the decimal. Now let us see whether it is working as an order. So 9 plus 2 is nothing but 1. 11. So 4 plus 0 is 4 plus 8 plus 6 is 14 plus 1 is 15. And 12 plus 6 is 18 plus 1 is 19. 19 means sum will be getting 1100 means 3. COT is nothing but 1. Now this works fine. Carry look and order. Did you understand these logical expressions? Huh? Did you understand the concept of carry, look and order? Is it okay? Huh? Like this, many fast carrying orders are there. Not only parallel order and look and order is there. Many are there. So for your understanding, I brought one order. Fast carrying order is carry, look and order. So the use of this carry, look and order is nothing but one. Pre-computing the values of C0, C1, C2, C3. If you look at this logical expression, C0, what is G0 is? A0 into B0. You are menuing A0 into B0. If you know what is A0 into B0, and this is P0 is nothing but one. A0 XR B0. C0 already you will be knowing for the first stage, correct? If you know this, you are computing the C0, no need of doing the operation. Here also, you can see C1 is depending upon what? The G1. G1 is nothing but A1 and B1. P1 is nothing but A1 XR B1. G0 is nothing but A1 and B1. Correct? B0. A0 and B0. And this also you know. Extra hardware come up to parallel order means extra hardware is required to computing the C0, C1, C2, C. Again, this gets also leads to some delay. But that delay will be less than what you are originally using as a parallel order. Each full order will take some delay, less than that. Okay, again, limitation of this carry look order means this is a 1. You see this C3, 1 input, correct? 2 input, 3 input, 4 input, 5 input. Imagine it is 8-bit carry look ahead order. What is C7 it should be? 1 input, 2 input, 3 input, 4 input, 5 input, 6 input, 7 input. There is no uniformity of the circuit. The different input gates you are using. Then that leads to problem of fan in and fan out problem. Okay, all gates will be having a typical value of fan in and fan out. If inputs you connect to the NAND gate is nothing but 6. For NOR gate it is 4. If you connect behind that 7 input or 8 input, it loses its character. It won't generate the desirable output. The strength of the output will be getting low. Then that you can't drive into the other circuits. So that is a fan in and fan out concept. I hope you understand the carry look and order operation using data. Now let us go with the next one. What is next example is magnitude comparator. Correct? Magnitude comparator. Write a program of data flow modeling of the magnitude comparator. So when you talk about the comparator, correct? What could be the outputs of the comparator? Comparator is nothing but it is a digital combinational logic circuit, which is used to compare the bits. When you're talking about comparing of the bits, you can compare bit, multi-bits. Multi-bit means a magnitude comparator. Magnitude comparator. Let us talk about 4-bit magnitude comparator. 4-bit magnitude comparator. The outputs to this comparator means equal, less than or greater than. If I write the block diagram to this 4-bit magnitude comparator. Magnitude comparator. These are the 4 bits. Shall I write the cross line like this? What this indicates? This cross line indicates variable inputs or multi inputs. Like this is nothing but A0, A1, A2, A3. If I'm talking about 4-bit. Again, this is nothing but what? B0, B1, B2, B3. A0, A1, A2, A3 is minute. B0, B1, B2 are the subtract. What are the outputs of this is nothing but? You can write A is greater than B. A is less than B. I can write A is equal to B. A is less than B. So when you say that A is equal to B, when you say A is equal to B, let us write A3, A2, A1, A0 is a manual. B3, B2, B1 and B0. When you say that this is equal, A is equal to B. When you say is equal to A is equal to B. If this is a case, right? A case is if I am writing all 1, 1, 1. This is 1, 1, 1. It is equal. All zeros, this is zeros equal. If it is 1, 0, 1, 0, again 1, 0, 1, 0, it is also equal. I can write this expression is A is equal to B, A3 x naught, A3 x naught, B3, correct? Into A2 x naught, B2, correct? Into A1 x naught what? B1 into A0 x naught, B0. If you remember 1-bit comparator, 0, 0 means what? A0, B0 equal. A1, B1 is equal. What expression you are getting A is equal to B means? XOR operation. Correct? If I write this is nothing but AI, in general, AI is equal to BI. If I put I is equal to 0, what I am going to get? A0 x naught equal I am talking about. A0 x naught XOR B0. Shall I take this is nothing but x naught? Right? So similarly, you can take x naught. If I is equal to 2, I is equal to 1, this is nothing but what? X1. X1 is nothing but what? A1 x naught B1. Again, I is equal to 2 means what? X2 is nothing but A2, right? And XOR operation of B2. I is equal to 3 means X3 is equal to what? A3 x naught B3. I can write this is XOR x naught into x1 into x2 into what? X3. Therefore, final A is equal to B expression what I can write? X3 and operation of x2 and operation of x1 and operation of x0. What is x0, x1, x2, x3 are? A XOR B, A XOR B. By substituting I, you will get x0, x1, x2, x3. If I am doing AND operation of this, I will be getting equal operation. Correct? Then how to write a logical expression, magnitude comparator logical expression for A greater than B. Let us take A greater than B expression. If I take A3, A2, A1, A0, B3, B2, B1, B0. Correct? This is A0 is LSB and A3 is MSB. Correct? Did you agree with me? A0 is LSB and A3 is the MSB. If my MSB bit is 1, A3 is 1, irrespective of A2, A1, A0, and if this is 0, irrespective of this B2, B1 and B0, always I can say this is A is greater than B. Correct? I can write this nothing. This is nothing but A greater than B. Correct? If I write A greater than B, one condition is what? A3 is 1 and B3 is 0, irrespective of A2, A1, A0. This is A greater than B. This expression I can write what? A3 is equal to B3 bar. You don't understand? This is one condition. If A3 is equal to B3, correct? If A3 is 1, B3 is 1, or this is 0, or it is 0. It is A3 is 1 or 0, B3 is 1 or 0. Then what I need to check? A2 I need to check. If A2 is 1, irrespective of A1 and A0, B2 is what? 0, irrespective of B1 and B0. This also I can say what? A is greater than B condition. Then how to write this expression is? I cannot plus, correct? Plus. What is both are equal means what expression is? This is A3 is equal to B3. What is A3 is equal to B3 means? X3. X3 into what? X3 into A2 B2 bar. Correct? A2 B2 bar. Again, what is next condition? You can go ahead.
Seconds. So please tell them to complete seconds.
Okay, it is notice that the online student, you should pay your second installment within today. In case if you are not paid, they are going to remove all your access. Okay, they are not going to share you the recorded sessions, notes. They are going to remove all your access. It is a kind reminder all of you to pay the second installment today, end of the day. Okay, this is second one, right? Again, how to check the A is greater than B is? If A3 is equal to B3, A2 is equal to B2, then I need to check what? A1. So this is I can write what? X3, X2, A2 into, sorry, A1 into B3. A1 into B1. Correct, A1 into B1 bar. Correct? Next is what? X3, X2, X1 into A0 into B0 bar. This is a logical expression for A is greater than B. Now to check for A less than B. How to check for A less than B? A3 bar B3. If this is equal means X3. A3 into A2 into B2, A2 bar into B2 plus X3 into X2 into A1 bar into B1 plus X3, X2, X1 into A0 bar into B0. Did you understand these are the logical expressions for the magnitude comparator? Now, can you write a program to this using data flow modeling technique? So write a data flow modeling 4-bit magnitude comparator using logical expressions. So what I need to write here, just delete this module, correct? Module name shall I use comparator 4. Comparator 4. What are the input is? A comma B. Output list are A, G, B I can write means A greater than B. And then A, E, B means A equal to B. A, L, B means what? A less than B. And here what are the ports or input ports? How many bit magnitude comparator we are designing? 4-bit magnitude comparator, read down to 0, A comma B. What about output? So it is a scalar or vector? Scalar, correct. We are checking. It is equal 0. If it is not equal, it is equal 1. It is not equal 0. So I can write A greater than B, correct. A equal to B, A less than B. Correct. Whether we are using any wire here, x0, x1, x2, then wire is nothing but what? x0, x1, x2, x3. Correct. Now what is the line I should write? Assign. Assign for what? First let me write first we'll generate a x0. What is x0 is equal to A of 0, right? XOR operation, B of 0, x0 means what I need to do, right? For this I'm taking the x0, then I'm taking the complement. A0 XOR B0 of what? Twiddle symbol. This is nothing but XOR operation, sorry. Correct? Now I should do it for what? X1. Now let us do it for X1. What is X1 is equal to? A1, B1, comma, X2 is nothing but what? A2, B2, comma, X3 is nothing but what? A3, B3. Then comma, then let me write end module and check for any syntax errors. No syntax errors. Now I need to write it for what? Assign. Let me write it for A equal to B. What is A equal to B is? X3 and of, correct? X2 and of, X1 and of what? X0. This is A equal to B. Again, assign A is greater than B is equal to what? Assign A is greater than B. What is A greater than B is? A of 3 and not symbol, right? Not symbol. A of 3. Okay, next. This is our operation. Okay. 3. Let me put this is x of x3. No, x3 it is. I am not declaring this as a vector. If I am declaring this is y 3 down to 0, correct? Then I should write what this is. X of 0, x of 1. Okay, let me write. No problem. What is there? Correct? Let me declare what? 3 down to 0 of x. Or to avoid the confusion. Then here, what I need to do? This is x of 0. This is x of 1. Is it fine? This is what? X of 3. This is x of 2 and x of 3. Now here what I need to do? X of 3, correct. This is x of 2. This is x of 1. This is x of 3. Now I need to write this is x of 3. What operation? AND operation. A of 2. Again AND operation. Not of B of 2. Again, this I am going to do R. Again, I am going to put it into the parenthesis. It is recommended to put into the parenthesis. Okay. Here also, if you want, you can put this into what? Parenthesis. This is one expression. I am going to put it into the parenthesis. Okay. Next, this is x of 3 under x of 2. Correct. Under A of 1 under not of B of 1. Correct. Again, this is R of x of 3 under x of 2 under x of 1 under A of 0 under not of 1. B of 1. B of 0. I am going to end this. Correct? This is for A is greater than B. Now let us copy the same and do the modification of this. This is for what? A is less than B. A is less than B means what? This is not. Then remove the not here. This is x3. Again here not. You remove the not. Here x3, x2, not of A1. Remove this. Again this is x3, x2, x1. This is a not. And remove the not here. This is nothing but A is less than A. Let us check for the syntax error. So no syntax error. Now we did the design file using data from modeling technique. Now we need to write the design, right? So test bench module TB then reg 3 down to 0, correct? A comma B then reg while A equal to B. Okay, greater than I'm writing. Okay, let it be. A equal to A greater than B. A equal to B, A less than B. Then comparator 4. This is a comparator 4. Let me copy the same. Comparator. I'm going to do the instantiation. Comparator 4. DUT. Let us go with the port connection by default. Then initial begin. Correct. Let us randomize it. A comma B is equal to dollar symbol random. Concatenation operator dollar symbol random. Let me give some delay. then dollar display of A is equal to percentage B, okay. Then tab space B is equal to percentage B, tab space A greater than B is equal to percentage B, tab space, correct. A equal to B, percentage B, tab space, then A less than B is equal to percentage B. What argument I need to pass? A comma B comma A greater than B comma A equal to B comma A less than B. Then end the module. Now let us run the program. So let me print A, B are in decimal. Now A is 2 and B is 4. A is less than B is equal to 1. Right. So can I repeat this? Repeat. How many times? Okay, let us repeat 10 times. Begin. Then I am going to end. So let us repeat this. This is less than,
हेलो
greater than,
हाँ यूज कहाँ पर है
less than, correct. This is greater than, this is less than, this is greater than, correct. This is less than,
अच्छा
this is also less than,
अरे तो कॉलेज
greater than,
यार वो फाइनेंस वाला मैं तो
less than,
करने की बोला था ना यार मुझे पता है
again this is also less than, this is also less than. Now this is working as a magnitude comparator, 4-bit magnitude comparator.
अभी मतलब
Did you understand the logic of this? How this will works? 4-bit magnitude
उनकी
comparator.
तो चालू होगी ना टीचरों की तो चालू होगी टीचर की तो मेरे ख्याल से कल से पढ़ेगी ना 11 से है ना तो मैं वही कह रहा हूँ
Say for example it is 8-bit
नहीं
magnitude
होगा
comparator.
यार
Is this logic expression will works?
फाइनेंस डिपार्टमेंट
It will not works, right?
फाइनेंस
Again, equal means what?
ठीक है तू जाएगा ना
X
जो मेरा
7
डिपार्टमेंट है उसी डिपार्टमेंट से पहले एक सिंडिक
X6 अंडा
स्टेयर पड़ता है स्टेयर के ऊपर जाएगा तो वो फाइनेंस
Did you
डिपार्टमेंट आ
understand?
जाएगा
So let us copy this code.
हाँ वो फर्स्ट
So
फ्लोर
this
है
is
सॉरी
4-bit
सेकंड
magnitude
फ्लोर सेकंड फ्लोर पर
Okay.
हाँ
What is the next question
लास्ट
is?
वाले में होगा लास्ट वाले एकदम
Okay, negative is triggering the flip now. The question is write a program of
तो एक वो फटाफट
data
ना मुझे
flow
कॉल कर
model
भले ऑटो ऑटो
of
चल जाएगा
negative
पैसे
edge
दूंगा तो
triggering
ऑटो चल जाएगा
D flip flop. Negative edge triggering the D flip flop.
हाँ भाई अभी जा फिर टाइम नहीं मिलेगा फिर वो तो वो
This is the one
लंच हो
question.
जाएगा फिर 1 बजे तो
And second one
अभी
is
निकल जाना
data flow modeling
तेरा
negative
भी
edge
वैसे भी
triggering
हॉस्पिटल तक लंच होता है फिर तू आ भी जाएगा
D
आधे
flip
घंटे में
flop. Use this to implement the D flip flop. Okay, this is the one question.
तो सफाई करते
Then I
सफाई
was talking about triple counters.
15 मिनट बाद निकल जाइयो
Okay.
फटाफट
So what is the negative edge triggering D flip flop?
तो जल्दी जा
Go to write a
जल्दी
data
जा
flow modeling for this negative edge triggering D flip flop. What is edge triggering flip flop will be? What are the types of edge triggering flip flop? Positive edge triggering flip flop and negative edge triggering. So output changes only whenever the rising edge comes, means positive edge. It will stay remain same until the next negative edge comes. Negative edge means output changes only transition happens 1 to 0. Negative edge comes. And it will stay remain same until the next negative edge comes. So edge triggering are quite advantageous than your master slave combination. Okay, one master slave combination is equivalent to one edge triggering flip flop. Master slave combinations work as a positive level and negative level. If master works at the positive level, slave works at the negative level. So using this combination is equivalent to one edge triggering flip flop. Okay. So your question is that you need to write a data flow modeling for negative edge triggering D flip flop. To write a data flow modeling for this negative edge triggering flip flop, you should know that logical expressions. And how you can write the data flow modeling technique is using what? Logical equations. or using logical equations is nothing but composing of expressions, operators, and the operands. So you need a diagram to this. If you know the diagram of this D flip-flop, you can model the what? Data flow modeling for the negative edge triggering D flip-flop. So let me show you. I think in the digital part, they used to write in terms of block representation, right? They write the box and clock representation. So positive edge and negative edge can be represented like this. Suppose I am writing positive edge. Positive edge D flip-flop is they will write like this, correct? With what is symbol of the clock is like this. This is a clock. This input is D. This is Q bar. So negative edge means there will be bubble here, right? There is a bubble. This is a clock. This is a D. This is Q. This is nothing but Q bar. You can understand. So, but if you break this block and see inside how these edge triggering flip-flops are designed. By using 3 latches. Using 3 latches, so we are designing the D flip-flop. Let us show. So this is a D flip-flop. So this is a D flip-flop. What D flip-flop it is nothing but negative edge D flip-flop. If you remove this inverter, now this will be working as what flip-flop? Positive edge. Positive edge. So edge triggering flip-flops are designed using 3 latches. What latch we are considering here? Yes or NAND latch or NOR latch? NAND latch. This is a 1 latch. This is another latch. This is another latch. 3 latches we are using along with few gates. Not gate. Now how this will work is, whenever negative edge comes, output changes. It will stay remain same until the what? Next negative edge comes. So in terms of your master-slave combination uses 9 gates. Your complete master-slave combination uses 9 gates. 9 including 3 input NAND gate and 2 input NAND gate. Look at this look at this edge triggering flip-flop. How many gates are I using? 1, 2, 3, 4, 5, 6, 7, 8 gates. And also it avoids the glitches. Edge triggering flip-flops are avoiding the glitches. Glitches in terms of digital vocabulary, there is narrow fuzzes. Unwanted signal that comes at the output. Okay, that is not wanted, that is unwanted signal. Small transient will happen at the output of the signal that we call it the glitches or racing problem. Okay, races. Okay, so your master-slave combination will be usually master will encounter with the glitches and edge triggering flip-flop will avoid the glitches. The way it is doing the mechanism of the edge triggering is, it will change this only when the rising edge comes. It will keep remain same until the next rising edge comes. Okay, one master-slave combination is equal to one edge triggering flip-flop. So this is my edge triggering what flip-flop it is? D flip-flop this is. Correct. Can you write a data flow model for this circuit? If I give the circuit, be able to do it. Correct. So here what are the inputs are? This is clear is the input, clock is the input, T is the input. What are the outputs are? Q is the output, Q bar is the output. Then what are the white data types are? C bar, S bar, S, R, R bar. Correct. Now to write the model to this. So what is the expression for the C bar is? Assign, correct? Assign C bar is equal to what? Not R, clear? Correct? Similarly for S bar. You write S bar, yes, R bar. Then you write it for what? Q bar. So that gives what flip-flop it is. D flip-flop. Write the test bench. Write the test bench to this D flip-flop. Okay. Did you understand this? Nectar skipping flip-flop. Then use this D flip-flop to make what? T flip-flop. How to make this T flip-flop? By putting the NOT gate to your output. Okay, this is your T flip-flop. This is your D flip-flop completely. Correct? Nectar is taking D flip-flop. The output is complemented here. If first clock when it is 0, correct? Q is equal to 0, here Q bar is 1. If I give the clock pulses, what happens? What input is going to this D is complemented. Q0 means it is complemented here. It comes 1 here. Now Q is equal to 1 and Q bar becomes 0. In the next cycle, clock cycle, D became 0. So that this is working as a toggling flip-flop. By simply connecting Q is complemented, that will be connecting into what? Input to the D. Now I am using the D flip-flop to get the what? T flip-flop. This is a question I was asking. Okay, the second question. The next question is use this T flip-flop. Use this T flip-flop to design the what? Ripple counter. Asynchronous counter or a ripple counter. Correct. This is asynchronous counter. The way we are giving the clock is what? Clock is feeding to the first flip-flop. Second flip-flop clock is from the previous hour. Now this is working as a 4-bit up counter. Did you understand? Now we should write a program for this. First to write the D flip-flop. From the D flip-flop, T flip-flop. Use the T flip-flop to design the what? Ripple counter. Asynchronous ripple counter. Okay, can you think of this question and write a program and bring me tomorrow? Huh? Write the D flip-flop, design file and test bench also. Use the D flip-flop to D flip-flop instantiate, then design the T flip-flop. Then you write the design for test bench for the T flip-flop. Then instantiate the 4 T flip-flop, design the what? Ripple counter. Are you understand what I'm expecting, what I'm asking you to do? Is it clear? You do this using data flow.
Sir,
So now your Verilog will supports what? Hierarchical modeling technique. Hierarchical modeling by hierarchical modeling. Combination, modeling, different modeling technique. So in data flow also you can instantiate, not only your gate level. You are writing a data flow for the D flip-flop. You can instantiate that D flip-flop to make the what? T flip-flop. Use the T flip-flop to design the what? Ripple counter. This is nothing but hierarchical. So we talk about top to bottom hierarchical or bottom to top hierarchical. This is nothing but what? I'm doing. Bottom to top. My bottom is D. Lip cell is D flip-flop. Use the lip cell to design the what? T flip-flop. Use the T flip-flop to design the what? Ripple counter. Now I'm going with what? Bottom to the top one. Hierarchical modeling. Did you understand? This is a one question. You can write. Okay. This is asynchronous counter. Now I'll ask you the synchronous counter. Another question is, you can try this also. Another question is synchronous counter. So this is a one. Synchronous counter. Before that, you see the question. What is the question is? This is the question. So a synchronous counter can be designed using what? Master slave JK flip-flop. Design a 4-bit synchronous counter. Circuit diagram for the synchronous counter and JK flip-flop are given below. The clear signal is active low. Data gets latched on the positive edge of the clock and then output of the flip-flop appears on the negative edge of the clock. Counting is disabled when the count enable signal is low. So write the data flow description for the synchronous counter Write the stimulus file that exercise for the clear and the count enable and display the output count. Q is equal to 3 down to 0 means 4-bit counter it is. So this is the asynchronous counter, and there is a small changes in the circuit is this output is giving input to this. You can consider this output is giving to input to this. This connection is not there. There is a wrong connection. Here also this output is giving input to this, and you remove this connection. Okay. Here also this output is giving input to this, remove this connection. Small typing mistake. This is synchronous counter with the clear and the count. Synchronous counter with the clear and the count enable. Okay. So this is nothing but what flip-flop it is. JK flip-flop. Master slave combination, JK flip-flop. You know, this is a master slave combination of JK flip-flop. This is your master, correct? This is your nothing but your slave. So you write the data flow model for the master slave JK flip-flop. Okay, instantiate that. Instantiating the master slave combination 4. You should design the 4-bit synchronous counter. Did you understand? So at least tomorrow let me the program, write the program to this two. Okay? Synchronous counter and asynchronous. Asynchronous using negative edge triggering T flip-flop. T flip-flop can be getting from what? D flip-flop. Synchronous counter using master slave combination JK flip-flop. Using 2 inputs. What are the 2 input is? Enable bar, enable count and here. Of course, clock will be there. Without clock, you can able to not do the counting, right? You write a program to do both the programs and then you bring it tomorrow. Okay. Now in this assignment, we have covered all the combinational part, right? Any questions are there? No? I think no. We are covered with all the questions and combination. Today you try this and bring me the program tomorrow. So with this we will wind up the session here today. Tomorrow we will continue. Okay. So now I request all of you to fill the attendance. Online student, any questions are there, you can please go ahead. Any questions from the online student, you can go in. Okay, let us stop the session. Today you try this too.